So like I said, I'll do some quick review of what we talked about last month to make sure we're on the same page in case you missed the first part of this. That's fine. My goal, I'm going to work with Jim here, who's going to help me make sure that we can get the PDFs out to you of the slide decks in addition to the recording, so you can click on the links that we have in the slide decks, to the resources that I present here that we can use. So the focus of this is going to be on kind of what I'm calling forced teleconnections. So teleconnection patterns that we observe in the subseasonal to seasonal climate system that we can really predict with more accuracy from a forced perspective. Traditionally, our teleconnection patterns that we talked about last month, and we'll do a quick review here, like NAO, PNA, North Pacific Oscillation, West Pacific pattern. Those types of teleconnection patterns are fundamentally internal to the extratropical atmosphere, and so prediction beyond, say, the limit of numerical weather prediction, so something like 2 weeks, is really challenging, although an area of ongoing research. So I'm going to focus on those areas today where we have some prediction skill beyond that numerical weather prediction limit. And so that's talking about Enso teleconnections, the El Nino Southern Oscillation, talking about MJO teleconnections. For that, I'm going to reach back to a really nice talk that my former boss and colleague, John Gottschalk from CPC, gave back in June, I believe. And so I borrowed some content from there that you'll see to kind of reinforce and connect that to what we're talking about here. We'll talk a little bit about stratospheric tropospheric coupling, so the role that sudden stratospheric warmings can play in enhanced prediction skill and generating and leading to preferred teleconnection phases at the surface. And then we'll look at some case studies and application. So I'll show 3 different things. One with respect to general winter reconstruction and attribution. One with respect to evolution of multiple MJO events in a given winter and how that impacted our extended range week 3-4 forecasts. And then one from this past winter on the sudden stratospheric warming and what role that may have played. And then I'll summarize and give a preview for our our November seminar, which is going to focus on stratospheric variability impacting winter climate. So that'll be exciting. All right, so backing up a little bit, I'm going to try to go through this review pretty quickly. So we talked about last month, synoptic and climate variations. We know that we have short waves and long waves, right? So what we fundamentally talk about in climate analysis, teleconnection analysis, is analysis of the low frequency standing wave patterns. And so we typically average over time and then conduct analysis that's trying to analyze the recurring patterns of variability in the climate system. Another way that we do that, as you remember from last month, that I won't go into here, is something we call teleconnectivity, right? So I can fundamentally look at 2 areas in the globe and I can see how well their climate systems are related to each other. All right, so here's kind of an overview from last month. This was a summary slide that we had last month just to kind of remotivate and keep this fresh. So 4 questions questions that help us answer the question about, should we care about climate? So one of my goals is to motivate interest in climate variability. All right, so is climate variability just a statistical residual or just noise? The answer is no. All right, so there are distinct and predictable low frequency variations longer than synoptic timescales. And we're going to talk about some of them today, our most predictable versions of that. Are these low frequency base state changes enough to affect daily weather? Yes, so this is really important because, especially in a changing climate, one of our interests is to understand how can climate and what role does climate and climate variability and change play in affecting daily weather? And that kind of comes into this 4th question, which is that impact large enough to be seen in weather events? And the answer is, it depends, but we can look for them. We can look for the fingerprints of climate forcings, whether they be interannual, internal variability, or whether they be forced on subseasonal, seasonal timescales like MJO and Enso, or if they be forced in terms of longer-term climate change. All right, so those are some important motivating questions. So teleconnections, that's what we're here to talk about fundamentally. What's the definition of phase relationship between geographically distant points? So this figure here is kind of the famous Walker and Bliss figure that's showing the NAO, North Atlantic Oscillation. So coming up on 100 years old, so almost 90 years old, pretty wild. So when we think about things like MJO and Enso, at first sometimes we think, in terms of teleconnections, it gets a little bit of a stretch from something like the NAO, which is looking at just a pressure difference between 2 points on the map. But when you consider something like Enso, which is fundamentally a relationship between or fundamentally the warming or cooling of the tropical Pacific and its attendant impacts on patterns of tropical convection. What you're looking at from a teleconnection perspective is you look at the phase relationship between anomalous convective variability and surface or mid-level climate anywhere on the globe. And so we're going to talk about those relationships here. And so that's how it fits in with our teleconnection framework. And in that context, I showed these last month. So these are 4 leading patterns from a teleconnection analysis. One thing I talked about a little bit last month is that our understanding of teleconnection patterns is somewhat fluid in the sense that we have different analysis schemes and frameworks that can give us slightly different answers depending on our application. So one such analysis that I did back in 2015. So this is basically the leading 4 patterns. And in this framework, you see Enso, this El Nino Southern Oscillation, low frequency, slowly varying month-to-month impact, this footprint, as distinct from these other 3 patterns of variability, all which are more internal to the extratropics, the North Atlantic Oscillation, the Pacific North America pattern, and then this North Pacific Oscillation, West Pacific pattern. That's really important for temperature variability over North America in the wintertime. The other thing we talked about, and this is going to be important when we come back to the influence of stratospheric warming, because a lot of this is talked about through the lens of the Arctic Oscillation here. So this is the Arctic Oscillation. You'll also see this sometimes referred to as the Northern Hemisphere Annular Mode, or the NAM, or the NAM, something you'll see in climates. We're not talking about the model. We're not talking about the short-term numerical model. We're talking about the Arctic Oscillation. We'll come back to this, but one thing that's important to remember about the AO, Arctic Oscillation, it's very highly correlated with the NAO. And in fact, it's not really possible to see them as distinct patterns of variability in the same analysis. So they are defined by slightly different analysis schemes, kind of going back to my earlier point about things being a little bit fluid in terms of teleconnection analysis, depending on your application. This, again, reminder from last month, because we're going to talk about this when we get to stratospheric warming. So let's put a pin in this. We'll come back. But the idea is we're going to look at how surface climate anomalies can be affected by the stratosphere. And then as a reminder, this is CPC's Teleconnection Web Page. So this link will be in the PDF and this gets posted if you're not familiar with it. One thing you can do to get more information about the teleconnection patterns in general, learn a little bit about how they're calculated, their climate footprints, their historical indices. You can click on this link, and then boom, it should give you this. And so you can get any information you want about them, the historical archive of all the indices, time series, their impacts, the calculation procedure, all that stuff's contained. There's really a lot of information on this website. It's pretty cool. A little bit dated, but relevant. Okay, so I wanted to include that here. The other thing we talked about last month that I think I just want to reiterate here is that there's a difference between what we call physical modes in climate analysis and climate dynamics and patterns of variability. So when I do an analysis to extract a pattern of variability, I'm fundamentally talking about a statistical manifestation, statistical relationship between points on a map. When I talk about physical modes, I'm now bringing that back. I'm trying to tie that to some physical process that's unfolding in the atmosphere. So we often want to develop, from my perspective, we want to develop analysis schemes that help to link them up. There's not a one-to-one relationship, but we can define analysis frameworks in which they kind of get a little closer. So a key physical mode that we're going to talk about today is Enso. How's that manifest in teleconnection patterns? In the 2015 analysis that I talked about, there's a standing Enso pattern, and then there's a relationship with the PNA in late winter and early spring. The MJO is interesting because that we see, depending on your analysis framework, you see an impact on the 3 main patterns of variability over the Northern Hemisphere, the PNA, the NAO, and the MPO. But then depending on how you construct the analysis, much like Enso in the analysis I'm going to show, you can also get a unique MJO response in a different analysis framework. So I'm kind of showing just how, depending on your application and depending on what you're trying to learn about the atmosphere, you can define an analysis framework that better helps you answer the question or challenge the question. Global change, this is really interesting, right? If you don't detrend analysis, again, depending on your framework, this can really get aliased into Enso patterns because Enso fundamentally is defined by a fairly large-scale warming of the tropics. And so that shows up as it can look similar to climate change, which is also a general warming of the surface, not just in the tropics but elsewhere. But that tends to be at least into that framework. So that can be a tricky part of analysis. And then this kind of internal extratropical variability that shows up as all of our extratropical patterns. When we look back to the seminal Marsden-Livesey patterns that are the basis for the current CPC analysis, it's very similar. The only difference is that that analysis framework was a little bit different, and it was one that was therefore unable to differentiate between Enso and internal mid-latitude variability. And so there was a lot more interaction with the PNA in that framework, as well as what's called the TNH, or the tropical northern hemisphere pattern, had very strong grounding in the tropics. So those two patterns, PNA and TNH, had very strong tropical SST footprints. I'm going to revisit this relationship between Enso and the PNA briefly in a bit. Very similar there. All right, so we're coming up on the end. We're getting ready to get into our new stuff here. Great. So predictable U.S. winter weather climate links. So long-term trends, okay, give us a predictable signal. And El Nino, La Nina, or Enso is important also. Subseasonal links to tropical variability. So this is looking at mostly MJO. And then finally, stratosphere and air-sea ice interaction. I'm not going to discuss the latter today. The one thing that I'm leaving out of this, because I would say we're at a state where we're not quite ready to bring to bear on operational prediction the role of air-sea ice interaction in seasonal prediction of extratropical teleconnection patterns. But that is something that is kind of floating around in the research domain that you might see something about. If you get into the literature, you might see some things around there floating around that we're not really prepared to present in this forum, but that is something that's there. I will touch on the stratospheric connections. There is ongoing work, and really there is effort to put that into our operational framework in the agency. Okay, so we're going to transition here into discussion of the Enso teleconnection. So this is from the NOAA PSL Physical Science Laboratory plotting tool. Very popular tool for climate folks to use. They use outside of climate, but it's a great tool to allow us to do quick analysis of various fields. And so I use it here just to show us what an Enso teleconnection looks like in its kind of rawest form. And so on the left here is a simple correlation between the Nino 3.4 seasonal index. So this is the basis for our determination of the state of El Nino, La Nina, state of the Enso system. So correlation of that index with 300 millibar geopotential height. So it's at that interface where we can see tropical extratropical connections quite clearly. And in this framework, you can see this wave train that propagates from the Pacific through the North Pacific, the equatorial Pacific, or the subtropical Pacific, through the North Pacific to North America. And so this is the kind of standing kind of canonical response that we see with respect to Enso. And it's quite predictable in the sense that we know Enso is ongoing. It's a very low frequency, so it doesn't change week to week. Changes very slowly month to month. And so we know that we can rely on, in this case, you have something like modest correlations over West Central North America of 0.4 to 0.5. And so we know pretty reliably, right, that something like 15 to 20 to 25% of the variance in those centers of action, that center of action is going to be explained by El Nino, which is just sitting there in the tropical Pacific, ready to be used for in a predictive capacity, right? It's not changing very quickly. We know the state of El Nino, so it gives us a boundary condition to really understand potential response in the extratropics. On the right is the same methodology, but we're just looking at temperature in climate divisions of the U.S., the contiguous U.S. And so you see, again, that kind of warm across the north, cooler across the south. What you'll notice, though, is these correlations are very modest. And this is an important point, because even though it's predictable, and the response from Enso is predictable, it explains a fairly small amount of variance. So what that means is there's still a very wide distribution, not much narrower than climatology, and only fairly subtly shifted from climatology. So by itself, these don't generate huge signals in temperature. Yes, they generate signals, but they're not huge. They're small relative to the interannual variability. And so it's just something important to keep in mind. When we transition to precipitation, this is the kind of classic precipitation, linear precipitation footprint. You have this kind of wet across the south with that little nose up in the central US and that little nose up on the southeast coast. And then you have dry in the Northern Rockies, and then to some extent in the Ohio Valley and parts of the Midwest. Of course, this is the El Nino footprint. So La Nina would be the linear opposite, right? So dry across the south, and then relatively wet across parts of the Ohio Valley, Great Lakes, and then in the Northern Rockies. What's interesting is that the Enso precipitation footprint is stronger than the temperature response. So that's kind of an interesting feature in the sense that in climate prediction in general, we tend to perceive temperature as being more predictable. That's definitely true in the especially when you consider long-term trends being lumped into that. When you remove the effect of long-term trends, then temperature prediction as a function of patterns of variability we know well in seasonal timescales isn't much better, if at all, than precipitation. So that's kind of an interesting thing that we see in respect to Enso. So that's pretty interesting. So real quickly, I want to talk about Enso versus PNA. So this is kind of an interesting topic because at one point it was kind of thought that the PNA was just existed as an extratropical response in the mid-latitudes to El Nino forcing in the Pacific. So we know now that the PNA, it's internal to the extratropical atmosphere. It appears as a pattern of variability without any MJO or Enso forcing, okay? But what I'm showing here, so on the left panel is the early winter, or November, December, January PNA pattern. The middle panel here is late winter, or the January, February, March PNA pattern. So I'm showing you, look at the top panels, they're very similar. If you look closely, you'll see a little bit more of a tropical grounding and pivoting around Hawaii, for instance, in the late winter pattern, very similar. And even the bottom row, okay, their 2-meter temperature footprints over North America are very similar. The nodal lines are very close. It's pretty similar. But the middle pattern is really interesting because the key takeaway here is that the tropical footprint, if you look across specifically the tropical Pacific, the footprint in the late winter PNA is stronger, quite a bit stronger than in the early winter PNA. And so that's that in this analysis framework, that's where we see the most influence of Enso on the PNA. So most analysis frameworks show the PNA being forced in part by Enso as a function of season. And the reason this is because of complex interaction between subseasonal and seasonal timescales. And this also contributes to something I'll touch on briefly in a second, which is flavors of Enso, and how that might affect the teleconnection pattern. And for reference, this upper right panel, this is kind of that standing low frequency Enso footprint. And so what you really come back to is that this kind of Nino 3.4 El Nino footprint that we see in the geopotential height field, you can kind of build this by taking into part the subseasonally varying and high frequency variability component of like the PNA that you see, and then superimpose that with a low frequency pattern, and then you get something like this. And so there's a lot of things going on there. It might have to do with, in part, the role of MJO biasing during Enso years. There's a lot of interesting things that can happen. I just want to point that out. So PNA can be influenced by Enso, but it's not the Enso response. So it's a standalone pattern of variability that we observe in the atmosphere from fall through the spring, regardless of Enso or MJO, but that during late winter and spring, it does carry a fair amount of the Enso teleconnection with it. Another interesting topic that comes up quite a bit is when we look at, so everything I looked at just before this was El Nino versus La Nina, was a linear correlation or regression type analysis. So I'm just, in that framework, by definition, El Nino and La Nina are just opposites. But they don't have to be that way. That physically doesn't have to be the case. So what I did here is I took all the El Nino events from El Nino La Nina events from 1981 to near present, not including last year because I wanted to get 13 cases in each one. So you have 13 El Ninos on the left, 13 La Ninas on the right. And the reason I showed this is because, to my eyeball, these are actually much more linear than even I was expecting. I mean, if you look at the main centers of action, southeast of Hawaii, the North Pacific, between the West Coast and Hudson's Bay, they're very, very similar. There are some differences over Eurasia, where traditionally we don't think about Enso footprints as much anyway, which is, again, interesting. But if you look at the North America, the Pacific North America domain, these are really quite linear. That's a very interesting finding just in the past 40 years, because there were at one point modeling studies that suggested they should be kind of linear, but then there's other more recent research has shown how there could be generation nonlinearities in the El Nino La Nina response, which is interesting. But generally speaking, they're pretty linear, but not exactly. And I'll show some tools that you can use in a local framework to assess this. The next thing I'm just going to talk about real briefly is what we call flavors of Enso. So the concept here is that while El Nino is the warming of the tropical Pacific, La Nina is the cooling of the tropical Pacific, the spatial distribution of those sea surface temperature anomalies are not the same in every case. And if you look at cases where, for instance, the warming is farther west in the Pacific near the date line versus right up against the South American coast and extending into the East Pacific, the idea is that the placement of the tropical anomalies, and then in turn the tropical convective anomalies, will generate a different response. Again, there's a history in the academic literature on how sensitive the extratropical wave response is to the placement of the tropical convection. But what I show on the right here is, so on the left, it's the same thing we saw before. This is just this is just kind of the Nino 3.4 teleconnection pattern that we can think of just from a broad linear sense. And then on the right is the correlation, what we call the trans-Nino index, which is the difference between the Nino region in the far East Pacific and near the date line. This does weight pretty heavily towards La Ninas. That's why it looks cold here. But it gives us a feel for, if you look at where these centers of action are, they're not perfectly orthogonal to or on the nodal lines of the main teleconnection, but they do show that if you superimpose these, you're able to shift the pattern left or right. And so there is some room for flavors of Enso. And how that physically is manifest in terms of that complex interaction between standing variability and the subseasonal kind of high frequency patterns of variability is complex and still an area of active research. But flavors of Enso is definitely an area where, if we're not careful, if you do kind of small sampling of events, it's easy to maybe overstate the case for flavors of Enso and how that affects North American winters. But that being said, just a broad survey of things suggests there's some room for this analysis and some room there where it might be useful in the future to help improve seasonal forecasts. So I just want to touch on that, because that's something that will come up as you look at winter forecasts, as you look at all kinds of things that are floating around, even in the media, about winter colder versus warmer than normal, and so canonical strong El Ninos versus weaker El Ninos farther west. Does this matter? How does this matter? Those are interesting topics. Anecdotally, on the flavors of Enso point, the one thing I like to also highlight is that we don't see it in the P&A framework. So the P&A and the Enso footprints in sea surface temperature are very similar. P&A is much weaker. So if I showed this map here in the middle column, middle row, if I showed that map for the Enso footprint, it would be spatially in the Pacific be very similar, just a lot stronger in the tropics. So even in that framework, the P&A versus Enso flavors doesn't support a broad flavors of Enso thesis, but there is certainly analyses that suggest this is something worth looking into. And so I wanted to put that out there, because it is something you'll hear about as you get more into climate variability and understanding some of the issues that we're grappling with. So one thing I wanted to show here, these are some tools for assessing local Enso impacts. So I'm just taking kind of big picture here. There's a few tools here I want to mention. So I linked them in here. So CPC has some great resources that use composites, which are what I showed in the second analysis. So that's looking at taking cases, adding them up, dividing by n, okay? And then regressions, which are, again, putting that line through your kind of y equals mx plus b solution to the problem. And then they have these box plots, which are pretty cool. I'm going to show an example of box plots in a second, but not from the CPC webpage. But they have the box plots for 102 climate divisions that can show you the relationships between Enso and temperature precipitation as a function of season. And the second tool is the local climate analysis, or LCAT. So here's the website here, if you're not familiar with it or haven't registered yet. Sorry, I had to take a drink of water. I just want to show a cool example of that. So this was just something fun that I did for this exercise. So one of the things you can do here, so this is looking at Baltimore Washington International Airport. So this is the closest international airport to my house, which is why I picked it, but you can pick any. And looking at seasonal snowfall for December through February from 1950 to 2020, and looking at this signal via the Oceanic Nino Index, which is CPC's official index for the monitoring and assessment of El Nino and La Nina. And what's pretty cool about this is that you see a robust relationship between the ONI, or El Nino, La Nina, and seasonal snowfall. So El Nino has a higher range, higher mean, higher extremes than La Nina. And there's other analyses you can do here, not just box plots, but you can do things that just show the composite response and then test it for significance, which is really powerful. And so in this case, for instance, you'll find that there is a very statistically significant relationship at this station at BWI between seasonal El Nino and seasonal snowfall in December through February, with El Nino generally favoring more snowfall. But as you think about this from a analysis perspective, you can see here all the overlap, right, that exists between this. So that's kind of what's going through before. So there's a signal, okay, and if you look at the averages here, or the medians, they go from 10 to 12 to 15 or something. So the signal's real, it's statistically significant, but it's small relative to the noise, right? So look at all your range of solutions that you have in any winter, and you can clearly see that the El Nino favors a little bit more, but you can get very little snow in El Ninos, and you can have really healthy snow years in La Ninas. And so again, it's that appreciation for understanding the relatively low signal to noise that we're dealing with in climate analysis in general. But anyway, you can do this with monthly temperature, max temps, min temps, and then we're working at Climate Services branch on a refresh, a rollout of an updated version of this in the coming couple fiscal years. But I want to show this is a powerful tool that you can use to understand Enso impacts locally in any part of the country. All right, so quick Enso wrap up before we move on. So it's the leading predictable teleconnection pattern in winter, forced by anomalous convection over the equatorial Pacific. Complex interaction among teleconnection patterns leads to confusion sometimes between the internal PNA pattern and the forced Enso response. That can be hard to differentiate. Enso is not a single SST or convective pattern. So there's complexity and nuance and a continuum. And so placement of SST anomalies can have some impact on the extratropical teleconnection. The extent, the size of that relative to the signal is complex, and I would say not entirely well understood. Interaction between the low frequency and the subseasonally varying patterns is important, and then this is also what can affect both Enso linearity and flavors of Enso. Precipitation pattern over cones is more robust, so that was a point I wanted to reiterate. And then these are the LCAT and the CPC attribution tools are useful for better understanding local climate impacts from Enso. Okay, so we're going to move out now onto our next kind of forced teleconnection patterns. So we're going to talk about the MJO. So again, a lot of this is courtesy of John Gottschalk from CPC, who did the Climate Services webinar back in June. And so a lot of this material is reviewed from that. So if you weren't there, that's why I'm doing it now, just to get our heads around this. So like Enso is the leading pattern of seasonal variability and triennial variability. The MJO is the leading pattern of subseasonal variability in the tropics. And so it's an intraseasonal wave that originates in the tropics. It results in many changes to atmospheric and oceanic variables, and it has a time period of approximately 30 to 60 days. This figure on the right here is showing it's typically placed, it's a two-dimensional index space, so there's two time series that comprise the MJO, and when you put them in a Cartesian coordinate system, you get this kind of circle that you can then demarcate 8 phases. That's what you're looking at here. So phases 2 through 1, you're looking at the propagation of the enhanced signal from the West Central Indian Ocean across the maritime continent out into the West Central Pacific. And then likewise, the suppressed phase shows a similar use for propagation. So that's what we're looking at here. And then in phase 2, of course, you start all over again. So the way this works is that when you have anomalous, it's really a heating source in the tropics, it generates a Rosby wave source. And so this is the way in which we get a tropical anomaly can generate an extratropical responses through this Rosby wave source term. And these are some seminal figures and papers that show how this looks in the case of anomalous heating, for instance, over the maritime continent or far western Pacific. So some of the largest changes are in the P&A sector, which is good for us because that's where North America is. Changes in the mid-latitude circulation can be similar to Enso, so I'll show some examples of this in a second. But of course, an axial time scale that's much shorter, so higher frequency. And then, like Enso, this is important. This is the focus of both of these webinars, which is winter. As like Enso, the strongest teleconnection occurs in the cold season, centered in winter. Similar to kind of, you'll pick up on this theme, right? We're still dealing with fairly low signal to noise, so each MJO occurs in different contexts, different Enso state, different background synoptic pattern, and so the impacts as we see them do vary a lot. Again, because it's a fairly small signal, but a predictable signal. So I'll mention this in a second. And so Rosby wave train response does in fact enhance or dampen ongoing circulation patterns. So being a superposition of that forcing on top of what's going on is how we get what we actually observe in part. So here is kind of what we call contemporaneous composite. So you take all the days that are in MJO phase 1, you add them up, divide by n, and boom, you get this plot on the upper left. Temperature anomalies, of course, do that for all the phases. And then you can significance test it. These are done, I believe this is done using a Monte Carlo method. But one way you can significance test is you randomly then pull the same sample a bunch of times, and you see how many times a random sample with the same sample size gives you a signal larger than what you got in your composite. It gives you an idea of how likely was it that what we're seeing is just by chance. So in this case, the purples are where it's very unlikely to be from chance, which is where we would say we're most confident this is a real signal. And so what you see is this warming in phases 4 through 6 across the eastern CONUS. And you see in this framework, the cooling doesn't show up as well, but you see it in phases 8 and 1 across the northern tier centered on the Great Lakes on average. You do the same thing for precip. And in this framework, the most consistent signal that we talk about in precip is generally the development of the Ohio Valley southeast dipole. So it gets, in the warm phase, it gets wet across the Ohio Valley, down the parts of the Mississippi Valley, and then relatively dry over the far southeast, including Florida. What's really interesting about MJO is that it historically has been discussed in relation to heavy precip events on the West Coast. In this framework, you don't see that as quite as well. You see some phase flip-flops, and what you see in terms of precip significance, it tends to be a little bit more spotty. But certainly phase 3 being wet on the West Coast is one of those patterns that you see, at least statistically, quite a bit. And then later in phase 8 tends to be drier. So that is one of the patterns we see that shows up, but it's depending on your exact analysis framework. MJO will depend on the kind of answer you get there. But certainly the MJO has been historically and can be related to Pineapple Express events that come out of the subtropical Pacific. So here is an example we call lag composite. So we don't always know exactly what the MJO is going to do. So, but because it's a tropical convective anomaly, it's going to lead to it will have a response that takes some time to propagate through the tropics. So we can leverage this in a lag perspective. And what you see here is this for late winter JFN, you have this really nice looking response. You have this anomaly west of Hawaii. Note this is similar but shifted west from the traditional Enso footprint and more like a PNA type pattern that generates this wave train into North America. And if you look over eastern North America, you get the development of the ridge at middle and upper troposphere and associated surface positive temperature anomalies. This is an analysis shows something similar. What I like about this analysis, in this particular case, it's a cluster analysis, and we're looking at this pattern here, which is a negative NAO. And we're looking at how often that pattern occurs associated with MJO. And what I like about this is that it shows that in most cases, the best response is in fact at lag. And so the reason this is important is that it means that it's really phase 6, 7 and phases 2, 3 that are doing the forcing. And what we observe contemporaneously is just a statistical manifestation of the tendency of the MJO to propagate eastward. But if it doesn't propagate eastward, if for some reason the anomalies stall or they weaken, the fact that they were there and generated a Rossi wave source can lead to this extratropical response nonetheless. And that's one of the things that you see here that's kind of neat. But again, it shows that you're more likely to have this occur following phases 5, 6, and 7, 6 and 7 at this kind of 10 to 20 day lag. And then the opposite is the case when that convection is over the Indian Ocean. You tend to see the opposite of this pattern. Or I shouldn't say that. This pattern occurs less frequently. And so that's really an interesting paper also that shows this in a slightly different way. All right, so a quick wrap before we get into stratospheric warming and some case studies. So MJO is leading mode of tropical subseasonal convective variability. Like I said, similar to Enso in terms of the physical mechanism. But it has a tropical response that is predictable and projects onto these mid-latitude teleconnection patterns that we've talked about. And it constitutes the leading subseasonal tropical, extratropical teleconnection pattern. MJO activity is generally more prominent during winters where Enso is weak to moderate or neutral. We've observed historically that in very strong El Ninos especially, but also to some extent very strong La Ninas, we tend to have less MJO activity, especially true with El Ninos. 2015-16 was a bit of an exception to that. We did have some prominent MJO activity during that winter. And MJO teleconnections, this is a key point here, are really an important source of prediction skill in the weeks 3 to 4 time period, especially for temperature. Although, like I said, precipitation is in there as well. Okay. All right. So our last 3 out of 3. This is our last kind of forced teleconnection pattern we're going to talk about before we get into some case studies. So sudden stratospheric warming. You'll see this a lot. This is the topic of Dr. Amy Butler's webinar next month. So I encourage you to register for that and to see that. I think there's going to be a lot of good information there. It's going to expand on this a lot. So it's kind of a teaser for that. So sudden stratospheric warmings are another potential source of subseasonal climate prediction skill. So what happens is when you have a sudden stratospheric warming, you tend to favor the negative phase of the AO, or as I said at the beginning, you'll also see this sometimes referred to as the NAM, or the northern angular mode, northern hemisphere angular mode. And that negative phase is more likely following a sudden stratospheric warming. So what we're looking at in this figure is a time, so the dashed line is the stratospheric warming, and time going forward to the right, backwards to the left, and we're looking at a cross section through the atmosphere. I put a black line here at roughly the position of the troposphere, the tropopause, to just let your eyeballs see what we're looking at in terms of the stratosphere and troposphere. And what happens is you have this stratospheric warming that propagates downward in the stratosphere. That is uncontroversial and happens all the time. But what sometimes happens is that we get these good coupling events that show up in the composites here as these kind of paint drips, you'll hear them called sometimes, that are associated with surface climate anomalies. And so this is important because if we have stratospheric warming or forecasting stratospheric warming, it tends to lead to this kind of general preconditioning over the next 1 to 2 months of the negative phase of the AO. Doesn't always happen. I'll just show you a great example from last winter, kind of where the timing was tough and tricky. This compendium here is a great source for information on this. So what does this look like on the surface? Here I think I plot the 0 to 45-day composites. So here, temperatures on the left, sea level pressure, mean sea level pressures on the right. And so what you see here, kind of take-home messages here, is that you generally favor cold, there's generally a cold composite in North America, but the stippling, which indicates significance, suggests that by far the stronger signal is over Eurasia. So that is a known feature. We know we have a much more reliable response over Eurasia than over North America. And so that is a key challenge when applying this in a prediction setting. So that's one thing I wanted to mention there. So kind of wrapping up some challenges and resources on sudden stratospheric warmings. So these are important potential sources of subseasonal prediction skill, but not all sudden stratospheric warmings result in a robust surface climate response. So that's really important, and there's ongoing research to refine our understanding of what the physical mechanisms are that are at play to help us better understand what events lead to a tropospheric response and which do not. And then work is ongoing in CPC to incorporate stratospheric predictors and objective subseasonal climate forecast tools. And like I mentioned, Dr. Amy Butler will be leading the next climate services webinar next month, November 16th, 3 p.m. Eastern. By then it will be standard time. And her topic will be the wintertime impact of stratospheric variability. So not just stratospheric warmings, but also strong polar vortex in the stratosphere, all that stuff. So I think that's going to be great. The 2 resources I have here for you, there's the Sudden Stratospheric Warming Compendium that Dr. Butler co-produced and hosted this website. So you can look at all the different events, their impacts, composite responses, again, to learn more about what's going on there. And then also CPC has a lot of good information on the stratosphere page, which you might find helpful. Okay, so with that, let's pivot into some case studies. I'm going to go through 3 case studies here. The first is looking at the 2013-14 winter. So at the time, this is a really interesting case. It was sort of well forecast. On the left is the forecast that we issued at CPC at the time, issued in mid-November for the winter season 2013-14. And this was kind of the pretty good forecast in the sense that there was this general consensus among the statistical and dynamical tools that we were going to see some colder than normal temperatures across the northern tier of the U.S., but really wasn't clear how extreme the winter would be. It ended up being 2 to 3 standard deviations below normal across parts of the upper Midwest. You can see here in absolute degrees Fahrenheit, we're looking at things like 7 to 11 degrees Fahrenheit below normal. Very, very impressive winter in terms of cold. And so this was kind of motivational for me at the time I was in grad school as well as working at CPC, so trying to understand what was going on here. One of the things that I did here was using teleconnection analysis, reconstructed the observed climate anomalies from that winter. And that's one thing that the teleconnection analysis can be really useful for. And so in this case, we reconstructed the upper left is the observed 850 millibar temperature anomalies. And then on the right is the reconstruction using 4 teleconnection patterns that I show here. 3 we've talked about, the MPOWP, which is really important for temperature variability over North America, the NAO, the TNH. In this case, this TNH here is not strongly related to tropical forcing. And then this is the East Atlantic pattern, which is sort of like an Atlantic analog to the PNA. That's something we don't talk about as much in North America. And the MPOWP was the leading contributor to colder than normal conditions that winter over the CONUS and especially the upper Midwest. This kind of red box is an area we were highlighting for some point analysis, as well as this TNH contribution. If you look at the month-to-month variations here, and then the total winter and standardized anomalies, and then you compare that to the CPC teleconnection indices. The WPO pattern from CPC is most closely corresponding to this MPO pattern, had these very strong negative projections, especially in December and February. In January was kind of interesting because it was in some ways a transition zone and a transition month. It was a little bit different. You can see the pattern in December and February is more similar. And then January was this kind of west-east dipole that was a little more transient, but had really cold temperatures here in the eastern U.S. So this is an example of how you can use teleconnection analysis to understand what patterns of variability are proximate causes for the surface climate we observe. And then we can, using that information, the next step is kind of understand how predictable they might be. And so certainly when you have things like Enso or MJO in these contexts, that helps you because we know they're predictable. It's also motivational to understand if these patterns appear in our models, how well modeled they are in terms of prediction skills, function of lead time, and what, if any, boundary conditions might lead to predictable and systematic biasing of these patterns during any given season. Okay, the next case study is an MJO-based case study. This is really interesting. So this was from the winter of 2017, 2018. And so this map on the left, this is that 8-phase Cartesian plane I was talking about before for MJO. So MJOs in this framework, they propagate counterclockwise. So a counterclockwise circle is what we like to see. And what we're looking at here is a winter that had really good MJO activity pretty much all winter. And so I'm going to kind of, I highlight on here kind of these three areas. We like to look in this up-down plane for major events because those, based on the consensus of the literature, are the main forcing events for a response. So I label them in order of when they occurred in time. So this one occurred in mid-December, 2 occurred in early January, and 3 occurred in early February. On the right here, I'm showing this kind of phase 7 response during early winter. And so you see this generation of the negative anomalies over North America at lag. So this is interesting. So mid-December, the enhanced MJO convective phase was propagating over the West Pacific. That's favorable for forcing a cold response over eastern CONUS. And this bottom row shows the tools that were actually in use at the time that we were issuing week 3 and 4 forecasts for this period. So this is pretty cool. So on the left, these are the temperature anomalies that were based just on the MJO constituent of a statistical model. The middle panel is using MJO, El Nino, La Nina, as well as long-term trends, and then converting it into probability space. And then the right panel is what happened. So in this case, spatially, it was on point. The magnitude was weak, weaker than observed, which we expect whenever we observe extreme events. And this was a fairly large-scale cold air outbreak from late December into early January. And so this wasn't a case where this was predicted and observed, and MJO played an important role. Likewise, the pattern changed in early January. In the midst of that colder than normal regime, the MJO enhanced phase was now over the Indian Ocean. That favored a pattern change. And so if you look at the MJO-based anomalies themselves, they ended up being quite good with the exception of the Great Basin area. The model probabilities themselves were a little bit damped over the central U.S. because of the influence of La Nina and trends, but nonetheless did quite well and captured, most importantly, that very intense pattern change over the eastern CONUS. So we're 2 for 2. All right, so like I showed, the MJO was gangbusters this winter. So it's back over the Western Pacific, and we're getting excited. The cold air is coming. It's coming again. Get ready. But this time, it didn't work. So this time, the dramatic pattern change occurred over the Western CONUS. And so it's nearly orthogonal to the expected signal. So you can see the expected signal here in anomalies and probability space. And what happened was kind of a clean east-west split. So that, generally we got the development of the ridging and warming in Alaska, discharge of Arctic air into the mid-latitudes, but it went into the western half of the U.S., which is not what you expect given the response to MJO. And so again, this shows that, it's useful, but it doesn't always work out the way we expect. Again, that's why, our model probabilities here were high, but they weren't 100. So this is actually about as high as you get. So this is about as big a miss as we're going to have over the Great Lakes, other than well parts of the plains. But that was a challenging forecast. So overall, MJO was very useful that winter, but in late winter, heading into early spring, that's where it didn't manifest itself the way it had earlier that winter. So there's that case study. The last one is the most recent one. This is from early this winter. So early 2021, we had a sudden stratospheric warming, disruption of the stratospheric polar vortex in early January. And this is neat because I think it gives us an opportunity to look at how our actual S2S forecasts, in this case I'm going to use weeks 3 and 4, how it unfolded in real time. And we could expand on this to include our monthly outlooks, week 2 forecast as well. And then also look at how is the southern stratospheric warming utilized? Did it play a role in observed climate anomalies or anticipated role in observed climate anomalies? So this figure here is showing this is the stratospheric warming that occurred in early January. You see the downward propagation through the stratosphere. Again, if you the tropopause is kind of in here, and then you have these kind of periods of connection. Interestingly, it's this period here in early to mid-February that was associated with the extreme Arctic outbreak over the central CONUS that was so impactful this past winter. So let's look at what happened here. So this is the first forecast that was issued by CPC for weeks 3 and 4 after the warming. Okay, and so here's the forecast on the left, and here's what was observed on the right. And this is actually the snippet from the forecaster discussion, which is pretty cool. So it mentions the southern stratospheric warming recently observed over the Arctic that resulted in a split of the polar vortex, potential for stratospheric tropospheric coupling, and that noting that also this would oppose tropical forcing. So we're piecing together. In this case, we're talking about La Nina and MJO, I believe in this case, definitely La Nina, that we're piecing together that these things are interrelated. So when you look at competing signals, they're being combined in statistical model space. And that we had previously had an ongoing negative phase of the NAO. So that might persist based on stratospheric warming. Now, what's really interesting is now we go forward 2 weeks, okay? So now we go forward 2 weeks into January 22nd. So this is the period targeting that big cold air outbreak. That's what we're seeing on the right here. This was the big one, okay? Now we'll look at what happened. We were forecasting not that. So what happened? So here's what's fascinating. So MJO activity MJO activity was weak at the time, but by this point, okay, this sudden stratospheric warming wasn't really having a manifest impact over North America, and the models weren't forecasting it to, so it was sort of written off, which is interesting because in real time, so it says the vortex was forecast to strengthen towards climatology, and any attendant impacts on surface temperature have not been noticeable in North America and are not expected over the forecast period. So what's interesting is, at the time, we were not attributing anything we were seeing here to stratospheric variability. Now let's fast forward a week. Now we're at late January. So by this point, the cold air outbreak is starting to creep into week 2, and now we know it's coming. So the models are responding, and then we still have a cold pattern that was observed, and the forecast was much better this time. And here we note that the MJO convection is going to serve to potentially reinforce any lingering impacts from the sudden stratospheric warming. And so I hope we're kind of giving you an appreciation for the complexities that are occurring as we have these different forcing mechanisms that are unfolding in real time and how we're trying to aggregate those. So I want to go back to something very quickly previously. What made this particularly tricky was understanding the extent to which this final kind of paint drip was being forced by the stratosphere, or was it coincidence that it happened to be superimposed on this, with respect to mid-latitude variability? So really interesting case to study here. And as we were watching it, as this was being a forecast unfolding in real time, it was some aspects of it worked well, some aspects of it didn't. So the sudden stratospheric warming was accounted for by forecasters. It was being utilized in the generation of the forecast, but with mixed success. And what's interesting here is I put a red line here. The skill scores for forecasts issued just after the warming were worse than those preceding the warming. So the forecasts that were issued the month before scored a little bit better than those that were issued in the month following that. So it's really interesting, and I think it highlights the need for ongoing applied research to better objectively incorporate these signals into our forecast process, to kind of understand what's going on. It's a very interesting case study, I think, here. So that's the third and final case study. So wrapping things up before we go to questions. So Enso, MJO, and stratospheric-tropospheric coupling are kind of 3 forced teleconnections that can lead to enhanced understanding and prediction of the climate system on S2S timescales. I have a lot of resources that I've linked throughout here, the SSW Compendium, LCAT, things from CPC, the Physical Science Laboratory plotting and analysis tool, lots of really good tools here to better understand and communicate local impacts of these teleconnections. And then lastly, another plug for the November 16th webinar by Dr. Amy Butler on the impact of the stratosphere and wintertime variability. I think it's going to be a great follow-on to kind of my little introduction here. I look forward to seeing what she's going to say. So with that, I will turn it back over to Jim and Andrea for questions. Thank you.
Yeah, well, he already put the plug in for next month. So let's go ahead and move to questions because we only have a few minutes. And I did put one in there that I get from, I've gotten a couple of times from our field offices out west here. If you can see that one, if not, I can read it.
I can see that. And let's see, it's CPC uses the term low frequency base state often on the MJO calls. Can you please define that?
Yeah. All right. Great. Yeah, I know that we got this question last month. We wanted to save it. So this is a great question. So when we talk about low frequency to high frequency, we're talking about the time scale in which patterns are changing. So when we look at tropical waves and tropical variability, there's a lot of our analyses decompose what we've observed in time as a function of frequency. So when we highlight things that are low frequency, it means these anomalies that aren't changing very often. So they're kind of stationary in the analysis. A lot of times that's related to El Nino, La Nina. So Enso is it's always associated with low frequency anomalies over the domain over which it has influence, which is much of the tropics, including parts of the Indian Ocean and Pacific. It doesn't always have to be that, though. Sometimes we see things from the Indian Ocean, like the Indian Ocean dipole. There are low frequency convection can often develop over the West Pacific. That's been an interesting source of research also, or topic of research, as to how that can happen sometimes and perhaps be important for mid-latitude winter. So yeah, low frequency means these are climate anomalies that are not changing, as opposed to high frequency, things like MJO and long and shorter time scales like Kelvin waves in that particular example. But in mid-latitude teleconnections, we would say things like there's often high frequency components to things like NAO, PNA, etc. But they also have low frequency components, a tendency for the NAO to be stationary with time. So you can decompose observed anomalies based on their time scale through frequency analysis. So low frequency is referring to those anomalies that are not moving very much and tend to be associated with Enso, but not exclusively.
Okay.
Thanks, Steve.
I'm showing a question that was in the questions panel, and it was about the LCAT URL giving a 404 not found error. And I just wanted to say that I checked that URL and it was working for me, so you might try giving it another chance.
Thanks. Yeah, let me pull that up. Where am I? Yeah, I pulled this right from the bar when I was doing it, so this should work. Yeah, let us know if this doesn't work. But yeah, I'm showing it here also, Jim. So yeah, I'm not sure why that wouldn't work.
Would you share your screen for LCAT to show?
Sure.
Thank you.
Let me see. I want to make sure. Here, I'll show this one. All right, so you should see it here. So this is LCAT, and if you don't have a login, you can create one. Go to register, and our colleague Jenna Myers in CSB will validate your account, and then you can go in there and get started. So if you're not familiar with it, I think it's a good opportunity to use it to dig in. Lots of good stuff in there, not just El Nino. That's one thing you can do climate analysis in. They do have things related to NAO and PNA as well. And then also you can do climate trend analysis in a couple different ways, which can be helpful depending on your application. So, and there's a lot of training materials in here also that you that you can lean in on.
Okay, and with that, I think since we are now 1 minute over the top of the hour, we probably should end the webinar here. Please join us next month for sudden stratospheric warming and stratospheric variability. Thank you so much, Steve. This has been great. Lots of good information. And again, Steve's presentations will also be available, not only this recording, but the presentations in PDF format will be available as well too. So you can get to all those links. Thank you, everybody, and have a great afternoon.